Hello everybody, welcome back. We spent a lot of time in the last video going over how to find eigenvalues and eigenvectors, and so now I want to get us to actually applying that. There's many applications of eigenvectors. It shows up a lot in signals processing, principal component analysis, where you look at the eigenvectors of a covariance matrix and you can separate components or estimate things. A lot of image processing. It shows up all over the place in quantum mechanics, things like that, but all of those are quite a bit more specialized. And so, following the hint of the book, I think I would like to do something a little more mathematically straightforward. However, this trick is something quite fantastic, and in the homework I'll have you do it. So I want to make an announcement real quick. Homework number 8 is going to be due Wednesday, which is of course the 15th. So make sure you remember that. I already posted it, so you'll have a week to work on that. And the second problem might take you some time, so make sure you get started on it a bit early. Anyway, I want to talk about this idea of diagonalization and sort of how and why it works, and give you an example of that and when it works in particular. So I want to come back to the example we had in the last section where we had this matrix A, and what did we do with it? We found the eigenvalues. So we took that characteristic equation, subtract lambdas down the diagonal, and then find the determinant, and then find the zeros of that when we set it equal to 0, and that gave us our eigenvalues here. And then for each of those eigenvalues, we found a basis for the eigenspaces that go with those eigenvalues. And for this particular matrix in this example, something really important and nice happened. This matrix, this is an n by n, it's a square matrix with our n being 3. So I've got the 3 columns here. Now the important, very nice thing that happened is if I look down here and look at the basis that we constructed for each of these eigenspaces, the dimension of those eigenspaces, remember dimension is how many vectors it takes to make a basis. Well, my 2 eigenspace has dimension 2. There's 2 vectors required to make a basis for it. And my 9 eigenspace has dimension 1. There was 1 vector required to make a basis for it. So what that tells us is that the dimension of those eigenspaces associated with that matrix were equal to n. I got as many eigenvectors in those bases. These are linearly independent eigenvectors. I got as many linearly independent eigenvectors as I do that r to the n that matrix gives me a transformation on. And if that happens, so let's make a little theorem here. Okay, so our big point here is that if I have that happening, so my eigenspaces, once I found bases for them all, I look at those bases, and if how many of those eigenvectors I got add up to the dimensions of that matrix, or just the n, then that matrix ends up being what we would call diagonalizable. Now what does that mean? In other words, that matrix can be written as some matrix times what we would call a diagonal matrix, and then times whatever that matrix on the left was, its inverse. So we'll say for some invertible n by n matrix, P and diagonal matrix D. And in fact, we can know an option, one of potentially many options, but an option for such a diagonalization of that matrix. So immediately a diagonalization that works is to make P have the eigenvectors from those bases of the eigenspaces. So as its columns, and then what diagonal matrix do I use? Make D have diagonal entries equal to the corresponding eigenvalues. So I can get this diagonalization thing. We'll talk a little bit more about what that lets us do. If I find those eigenvectors, the ones that I made the bases of the eigenspace, and I have enough of them to fill out the columns of a matrix that's the same size as my original matrix, then I can get this diagonalization of that matrix. And so let's see an example. So let's go back to our matrix A that we was using last time. Let's go back to this. So here, my eigenvalues were 2 and 9, and for the eigenvalue 2, a basis for that eigenspace was these two vectors. And then for that eigenvalue 9, a basis for that eigenspace was this vector. So what that tells me that original matrix is going to equal, I'll make my P matrix be those eigenvectors in those bases. And then my diagonal matrix in the middle is just the corresponding eigenvalues. Well, these two columns of this new matrix were from the 2 eigenspace. So that means my first 2 diagonal entries should be 2s. And then this third column came from the basis for the 9 eigenspace. So that means I want my third diagonal entry to be a 9. And that's a diagonal matrix, in case you forgot what that means. That just means everything that's not along the diagonal has to be 0. And then what matrix goes here? Well, that's just going to be whatever this matrix, whatever its inverse is. So then, if I wanted to, let's clean this up a little bit. Here's that diagonal matrix. If I wanted to, I can compute what the inverse of this matrix here is. Maybe we should compute that. So off to the side here, real quick, let's compute the inverse of that matrix. So that was down the columns 1, 2, 0, negative 3, 0, 1, and 1, 1, 1. Remember, if I want to compute an inverse, the way we did that most was attach an identity matrix to it, and then perform a row reduction all the way to the end so that we get the identity matrix on the left side. And what we end up getting is this. So that matrix at the end, there's the inverse there. So if you have to, you can compute an inverse, plug it in right there. So that original matrix we had, that matrix A, up here, can be factored as the product of these three matrices, where we call that one the P, this is our diagonal matrix, and this is just P's inverse. Okay, so what's the use of that? And this is what we would maybe call a dynamical system. So we have a transformation. Let's say that takes me from whatever dimensions back onto whatever dimensions. And we're interested in powers of that transformation. In other words, I look at where it sends some point, but then I want to know if I apply the same transformation again, where does the point go? And if I want to apply the same transformation again, where does the point go? And on and on and on, right? In other words, I'm interested in applying that transformation many, many times. Well, if that's a matrix transformation, which all our linear transformations from Rn to Rn are matrix transformations. Linear transformation. If that's a linear transformation, then applying that transformation whatever number of times I want is the same as left multiplied by that matrix that many times, which would just be left multiplied by that power of that matrix. However, we have a difficulty. Computing powers of matrices is hard. Matrix multiplication doesn't happen coordinate-wise. So in order to compute a power of a matrix, I would need to do, okay, take my matrix A, multiply it by another A. Well, there's my A squared. Now I need to do another matrix multiplication by A again to get my A cubed, and then another matrix multiplication by A again to get to my A to the 4, and I have to keep going to whatever nth power of the matrix. And so there's many, many, many operations going on in order to get there. It's very inefficient. However, this diagonalization gives us a shortcut. So what's the use of this? If A is diagonalizable, in other words, we have this diagonalization. I have that invertible matrix times that diagonal matrix times whatever that invertible matrix's inverse is. If I can factor A like that, then if I want to take a power of that matrix, multiply it by itself as many times as I want, notice what ends up happening is if I factor A like that, and now I have n many A's, right? This is just A times A times A. Notice what happens. Matrix multiplication, while it's not commutative, I can't flip the order around always, it is associative. I can move the parentheses around. In other words, I could multiply that P inverse and P together first, and then there's going to be a P inverse at the end of the last factor before this one. Those I could multiply together first, and I could do that all the way through. There would be a P starting the next one after this one. I could multiply those first, but then that just gives me an identity matrix in the middle there, which won't do anything, and so all that stuff will cancel out. And so what you end up getting is P, and then you have a bunch of D's left in the middle, and I have as many as I originally started with, so you would end up with a D to the n times that P inverse at the end. There's one left over there, and there's one P left over at the start. But this is incredibly nice because one thing you proved in your homework was that for a diagonal matrix, if I only have non-zero stuff down that diagonal, if I do matrix multiplication with diagonal matrices, then the multiplication does happen coordinate-wise. And so if I want to take a diagonal matrix, let's call it A1, A2, A3, times another diagonal matrix, let's say B1, B2, B3, then the multiplication really does happen coordinate-wise. Whoop. So you did this in the homework, and we talked about it for any number of dimensions. And so what that means is, once I know what that diagonal matrix is in the middle, I can actually take powers coordinate-wise. Which requires way less computation than trying to do in many matrix multiplications. Instead, I just take in many numbers down that diagonal and take them to the nth power. Now I just realized I made a little bit of a mistake here. I'm using the n not to mean the dimensions. I'm just saying whatever power of that matrix I want. This n doesn't depend on the fact that we were calling A n by n matrix. I accidentally used my letter for two different things. So hopefully that didn't cause any confusion. Feel free to email me questions if you've got them. And now I want to talk about why this works a bit. So why, or maybe slash how. So let's look at that idea again. So I have this matrix and it factors like this, where I've got this diagonal matrix in the middle, I've got that invertible guy, one on each side, inverse. Now let's think a bit about what this means. If A has as many independent eigenvectors as it has columns, that means that if I think of A as a transformation, right? A has enough eigenvectors. If A has n independent eigenvectors, an independent set is a basis for something, some subspace. But if I have n many of them, that subspace is all of R to the n. So A's eigenvectors are a basis for all of R to the n. In other words, I can think of my whole R to the n space here. I can think of it as having whatever those eigenvectors are as its basis. In other words, every point in R to the n, I can think of it as some linear combination of those eigenvectors. Let's say that point was here. And so I can think of every point as coordinates multiplied by those basis vectors. And then I can think about what does the transformation do to those points, that left multiplication by A. So if I have that point x and I left multiply by that A, perform this transformation, I can think of what the transformation does in terms of that basis. And then what's happening here geometrically, intuitively, to see that this factorization works is that, well, P would be the matrix that sends, remember, the columns of the matrix tell me where that matrix would send those original standard coordinate vectors. Well, that means that P's inverse would take these coordinate vectors and send them to our usual coordinate vectors. It would send them to the usual coordinate vectors. And then I'm looking at the usual coordinate vectors. Now I'm looking at the usual coordinate vectors. And then this matrix just has those eigenvalues, which will then just scale those standard coordinate vectors. So then these will get scaled. And then this would just send these back to those basis vectors we were talking about before, except scaled now. And in terms of a transformation, that's got to be what my original transformation I was interested in would do, because if I'm thinking of those as basis vectors, remember, what is an eigenvector? It is something that transformation just scales. And so if those eigenvectors are forming a basis for the entire space, whatever my R to the n is, then once I define how those are getting scaled, for a linear transformation, that's going to define what I do on everything. And so this works out very, very nicely for us. Now, a couple more things. One, I want you to finish the homework, but in the homework, I'm really having you just do what we did with A here. So once you can find all your eigenvalues, find bases for the corresponding eigenspaces, and then find that diagonalization. Now, might want to review finding an inverse, because checking this multiplication and make sure that when I multiply those three matrices in that order, I get back to A is pretty useful. That's most of the homework, and then I have you doing an application where I want you to find the powers of a matrix by using this trick. So again, if I want to find some power of a matrix, now here I'm using the n to mean what power of the matrix I want, not the dimensions of that matrix. So let's pretend I used a different letter. This formula here is very, very useful. And so I'll have you apply that and do something pretty exciting. Now, one more additional little thing I wanted to talk about that's not really necessary, but I realized I made reference to it in the homework, so I wanted to show you really quick. Let's call that a shortcut. For a 2x2 inverse. You can get a formula for the inverse of a 2x2 matrix as long as it's invertible fairly easily, because with a 2x2 the algebra doesn't get too nasty. So suppose we have this 2x2 matrix and that it's invertible. If I wanted to invert it, what do? We attach the identity matrix to it, and then I run that row reduction. Now, the row reduction is algebraically going to be a bit messy, so let's just pretend we did that. And what you get is this. So that gives us a little bit of a shortcut formula if you're just doing inverses for a 2x2 instead of running the row reduction every time. That means that if I have a 2x2 matrix and it's invertible, its inverse is going to be this matrix right here. But notice, each of these entries is just getting scaled by the same 1 over 80 minus BC. And so I can pull that number out. And then what's going to be left is D minus B minus C A. And so if I want to do an inverse for a 2x2, what can I do? These entries just get swapped. And then my other diagonal entries just get made negative. And we end up here, and then that whole thing is getting scaled by 1 over 80 minus BC, but remember, that's just the determinant. So actually, that gives us a pretty good shortcut. Swap these two entries, make the other entries negative, divide by the determinant. Anyway, I used that in part of the outline in that second homework problem I want you all to do, and I wanted to make sure you recognize where that comes from. Anyway, that finishes us up pretty good for now, and I'll see you next time.